Welcome back to another deep dive. Today we're taking on a stack of sources that honestly might fundamentally alter how you picture the entire universe around you.
Yeah, it's a dense one today.
It really is. So whether you're joining us to catch up on some highly unconventional theoretical physics or, you're just fascinated by how human perception shapes our reality, grab a seat. You are the third person in this conversation today.
And you'll definitely want to settle in for this one.
Right. Our core text today is this highly eccentric, deeply layered draft blog post. It's titled, Mr. Einstein's Slacking Off 119.
Which, the title alone signals that we are dealing with a completely non-traditional approach to established science here.
Definitely.
The document itself is this incredibly dense synthesis. It weaves together complex physics diagrams, linguistic theory, deep philosophical arguments, and even transcripts from an English audio segment.
And we can't forget the ancient Chinese history.
Right, yeah. Most unusually, it uses analogies drawn directly from the political structure of the Han Dynasty to explain dimensional geometry.
Which is wild. The juxtaposition of, Maxwell's electromagnetic equations with ancient military generals is definitely jarring at first glance.
It takes a minute to wrap your head around.
It does. So our mission today is to cut through that eccentricity and synthesize these notes into a singular cohesive understanding, because the author is presenting a radical reimagining of how we perceive space and time.
They are actively challenging Einstein's traditional model of relativity.
Exactly. But crucially, they're attempting to dismantle Einstein's geometric framework without changing a single physical result that we observe in real-world experiments.
That's the real kicker.
Okay, let's unpack this, because to even begin grasping how the author redefines the geometry of the universe, we actually have to start with, of all things, the study of language.
Yeah, linguistics. The author grounds their entire argument against the current physics paradigm in this linguistic concept known as metonymy.
Metonymy.
Right. So metonymy is a figure of speech where you substitute the name of an attribute or a related concept for the thing itself. And it's based entirely on proximity.
Like the kettle example in the text.
Exactly. The text provides a really straightforward example, saying, the kettle is boiling.
Which we say all the time.
All the time. But everyone understands that the metal kettle itself is not literally boiling.
Right, the metal isn't bubbling.
The water inside the container is boiling. But because the container and its contents share spatial proximity, we just conflate the two for conversational efficiency.
It's just easier to say.
Exactly. And that represents spatial metonymy.
But the author doesn't stay on spatial metonymy for long. They quickly pivot to temporal metonymy.
Yeah, which deals with proximity in time.
Right, confusing a cause with an effect or just muddling the sequence of events. And they apply this cognitive blind spot directly to how we observe the physical universe.
Which is where they bring in the concept of the postal ray.
The postal ray. I love this visual. Let's picture a scenario on a standard, flat, Cartesian coordinate system, like the graphs we all drew in high school.
Sure, the x and y axes.
Right. So you're watching a train move at a velocity of 0.6 times the speed of light, so 0.6 c.
Fast train.
Very fast. And it passes a specific marker on the x-axis, say x equals 10, at a very specific moment, t equals 0.
Okay, so when you register that event, the train passing that specific marker, you are not experiencing it instantaneously.
Even though it feels like you are.
Exactly. The visual evidence of that event has to cross a physical distance to reach your point of observation. It is carried by light.
And the author labels this incoming light a postal ray.
Right, likening the speed of light to a mail delivery service. The light is merely a letter carrying data about an event that has already occurred in the past.
It's already done. The train is gone.
Yes.
So the postal ray arrives carrying historical data, but we treat it as breaking news.
What's fascinating here is how the author connects this physical delay right back to linguistics. We fall victim to temporal metonymy.
Just like the kettle.
Just like we confuse the kettle with the boiling water, we fundamentally confuse the arrival of the delayed light information with the actual present state reality of the universe.
Right.
Our brains, and by extension our traditional models of physics, take this delayed mail, read the time and speed data stamped on it, and plot it onto a flat Cartesian map.
And then we confidently label that flat map right now.
What we do, we are projecting outdated information onto a two-dimensional grid and declaring it an accurate picture of the present moment.
It's like reading yesterday's newspaper and thinking it's a live broadcast.
That's exactly it.
So to demonstrate how different perspectives handled this delayed information, the author introduces this cast of characters from the Han Dynasty.
Which is such a unique approach.
It really is. Using historical figures to map out dimensional physics sounds completely absurd at first, but it actually creates a surprisingly vivid framework for understanding observation.
It really works.
It does. Let's look at Observer 1. The author maps this perspective to Han Xin, who is a brilliant military general. The text refers to him as the Train King.
The Train King.
Right. So Observer 1 represents a moving state, velocity, and they're restricted entirely to a one-dimensional x-axis within Maxwell's electromagnetic field.
Analyzing Observer 1 through the lens of Han Xin is quite revealing, because a general on the battlefield exists in a hyper-localized, closed world.
They only see what's right in front of them.
Exactly. The text describes this state as being entirely consumed by self-evaluation and local peer evaluation. Han Xin measures his worth strictly against the other commanders immediately around him.
So translating that back to physics.
Observer 1 is the standard, subjective, local view. It's a single frame of reference moving along a flat line. It's capable only of evaluating its speed and position relative to other objects sharing that exact same one-dimensional line.
It has no idea what's happening outside that line.
Right, it lacks any broader awareness of the field.
So Observer 1 is completely confined to the trenches of the x-axis. But stepping back, we encounter Observer 2.
Xiaohe.
Yes, the author uses Xiaohe to represent this perspective. He was a crucial statesman, like the ultimate administrator of the Han Dynasty, operating far away from the front lines.
Which means Observer 2 is stationed on the two-dimensional Z-plane. And importantly, Observer 2 is at rest.
Not moving.
Right. Their velocity is 0 within the Maxwell field. They are watching the x-axis from a distance, perhaps positioned at, let's say, y equals -100.
Sitting at a desk looking at the whole battlefield.
Exactly. And because Observer 2 is removed from the action, the postal rays, the light carrying data from various points along the x-axis, they have to travel varying distances to reach them.
Because they're not on the line anymore.
Right. The information does not arrive all at once. It arrives staggered. A report from a nearby point on the x-axis arrives quickly, while a report from far down the line takes significantly longer.
So Observer 2 acts as what the author calls the Cartesian reconstructor.
Yes. They receive this staggered mail, and they calculate the information lag. They take the known distance the light traveled, denoted as d, and divide it by the constant speed of light, c.
Distance divided by speed. Just basic math.
Exactly.
So they figure out exactly how late the mail is, and then they use that mathematical calculation, d divided by c, to retroactively adjust all the incoming data.
By applying that formula, Observer 2 artificially neutralizes the delay. They take this chaotic, staggered influx of delayed light and mathematically force it into a perfectly straight, flat Cartesian x-axis.
They'll clean up the mess.
They do. They construct a logical timeline of what happened and when it happened. However, this timeline is a retroactive fabrication.
It's an illusion.
It is a purely calculated simultaneity. Observer 2 builds a flat model of reality entirely out of adjusted, delayed mail. And that, the author points out, is the foundational perspective of classical mechanics.
Here's where it gets really interesting.
Oh, yeah.
The author insists that Observer 2's flat, retroactive map is still fundamentally flawed. To see the actual structure of reality, we must shift to Observer 3.
The Emperor.
The Emperor himself, the founder of the Han Dynasty, Liu Bang. Observer 3 is not on the flat Z-plane at all. They are positioned at a massive, complex depth, situated high above the plane on the Z-axis.
At a coordinate, the author specifies as z equals 1,000.
Right, Z equals 1,000. So Observer 3 is looking down at the flat Z-plane, where Observer 2 is busy doing all the retroactive calculations.
The author designates Observer 3 as the higher dimensional describer. And from this elevated three-dimensional vantage point, the rules of reality change drastically.
The math completely changes.
It does. The calculated retroactive timeline created by Observer 2 holds absolutely no weight here. For Observer 3, the concept of simultaneous is governed by a strict, unforgiving geometric law, which the author calls equal past.
Equal past. The idea that simultaneity requires an equal past completely breaks the Cartesian grid.
It really does, because it demands that the travel time of the information, the physical journey of that postal ray through space, must be absolutely identical for two events to be considered truly simultaneous.
No retroactive math allowed.
None. If the light took the exact same amount of time to reach Observer 3, those events share an equal past. In mathematical terms, the text states this absolute rule, as constant past equals constant radius, or r.
So the physical distance from the higher dimensional observer to the events must be perfectly equal.
Exactly equal.
That brings us to the core of the diagrams that are scattered all throughout the source material. Imagine you are observer 3 hovering up at z equals 1,000.
Looking down at the map.
Right. You look down at observer 2's perfectly flat Cartesian x-axis, and you attempt to draw lines of equal distance, a constant radius r, to every point on that line.
Geometrically, it's an impossible task.
Completely impossible.
The mathematics simply do not allow it. A straight line dropping directly down from z equals 1,000 to x equals 0 will always be geometrically shorter than a diagonal line reaching out from z equals 1,000 to, say, x equals 100.
Basic geometry.
Right. And because the distances vary, the travel time of the light varies. Therefore, a flat Cartesian plane cannot possibly satisfy observer 3's rule of equal past.
It fails the test.
It is structurally incapable of supporting true physical simultaneity from a higher dimensional perspective.
So the flat map fails the test of equal distance. To solve this, the author proposes that the geometry of the observation map must fundamentally change.
It has to bend.
Right. To maintain that equal distance or to ensure the postal rays all travel for the exact same amount of time, the points cannot remain on a flat plane. The author describes the space actively bending.
Bowing upward.
Yes, it bows upward into what is referred to as a complex or imaginary dimension, which is denoted by the Greek letter tau.
Now, in mathematics, when real number equations break down or result in impossible geometries, we utilize imaginary numbers. These are axes that exist outside our standard three-dimensional perception, and they resolve the mathematics.
That fix the math.
They do. The author employs this tau dimension to illustrate that space must literally curve outward into an unseen dimension to maintain a constant radius for incoming light.
Which forms a shape.
Yes, this upward bending creates a dome-like structure, which the author specifically names the 323 attosecond spherical cap.
An attosecond. That is an almost unfathomably small unit of time. It's a quintillionth of a second.
Extremely small.
So specifying 333 attoseconds highlights just how precise and localized this geometric curving is at the quantum level of light observation.
It's happening on a microscopic scale.
Right. So the historical map that the Emperor, Observer 3, is looking at is not a flat piece of paper. It is a curved, three-dimensional dome screen of equal past information.
To really anchor this concept of rigid geometric rules dictating reality, the author briefly introduces the mechanics of a simple pendulum.
I found this part really helpful.
It is. So the period of a pendulum, the exact amount of time it takes to complete one full swing, is strictly determined by its length.
Nothing else matters.
Exactly. You cannot alter the time of the swing without physically altering the length of the string.
The pendulum proves that you cannot cheat the underlying geometry of a system.
It serves as a perfect analog for the spherical cap. Just as the length of the pendulum string dictates time, the constant radius r dictates the constant past. You see, if the radius must remain rigid to achieve simultaneous observation, then the space itself must curve to accommodate that rigidity. The geometry governs the physics, forcing the flat plane to bow into the imaginary tau dimension.
So what does this all mean? We have navigated through temporal metonymy, we've analyzed the viewpoints of Han Dynasty historical figures, and visualized space bending into a 333 attosecond spherical cap.
It's a journey.
It really is. The ultimate question is why the author goes through this immense complex trouble to redefine the basic geometry of space and time.
The answer lies within the transcripts of the English audio segment included in our sources.
The audio, right.
The audio delivers this critical piece of information. If you run physical experiments measuring light and motion using this new spherical cap model, the results observed in the real world are identical to the predictions made by Einstein's theory of relativity.
Identical.
Identical. The text explicitly notes that no fringe shift is ever observed in these experiments. In a laboratory setting, Einstein's math and the author's geometry produce the exact same physical outcome.
The destination is exactly the same. But the route taken to get there is fundamentally different.
Completely different.
Einstein built his model of relativity on the assumption of Minkowski spacetime, which operates on a fundamentally flat background. To make the math work and ensure the speed of light remains constant for all observers on that flat map, Einstein had to propose that the variables of time and space are flexible.
Right. Einstein resolved the inconsistencies of light observation by stretching time dilation and compressing space length contraction.
Time gets stretchy.
He proposed that the physical realities of time and space must warp in order to preserve the flat geometry of the coordinate system.
But the author's spherical cap model flips that paradigm completely upside down.
It does.
Instead of breaking time and space to keep the map flat, this model keeps time and space rigid and constant, and instead curves the descriptive map into a complex geometry.
The space and time do not undergo physical dilation or contraction here. Instead, the baseline assumption that we operate on a flat Cartesian plane was flawed from the very beginning.
The map was always curved.
Exactly. By moving the mathematical burden from the physics of time into the geometry of an imaginary dimension, the author achieves the same constant speed of light without requiring time to slow down.
The English audio transcript provides an exceptional analogy for this shift. It describes it as a potential Copernican revolution of complex geometry.
That's a powerful comparison.
It really is. When Nicholas Copernicus challenged the geocentric model of the universe, he didn't alter the physical composition of the stars or the planets. The celestial bodies remained exactly where they always were.
Copernicus merely relocated the observer.
Right.
By moving the vantage point from a stationary flat Earth to a sun-centric solar system, the wildly complex and seemingly erratic orbits of the planets suddenly made perfect, elegant, geometric sense.
He changed our geometric understanding of our position relative to the cosmos.
That is precisely the shift the author is proposing with the spherical cap. We don't need to discard the highly accurate physical results of relativity.
The math still works?
The physics work. We simply need to stop forcing those results onto Observer 2's retroactive, flat Cartesian spreadsheet. We need to recognize that we are actually standing inside Observer 3's curved dome, where space naturally bows into the tau dimension to keep the past constant.
It's a profound reframing of classical mechanics. It suggests that a century of theoretical physics has been dedicated to explaining the distortions of a flat map, rather than recognizing the curvature of the actual territory.
That's exactly what the author is arguing.
So as you, the listener, navigate your daily life, consider the profound implications of this framework. You manage your schedule, you plan your commute, you attend your meetings, operating entirely on the assumption of a flat Cartesian grid.
We all do.
We check our watches and look at our surroundings, assuming everything we perceive is happening simultaneously on a flat plane. Yet the math behind the spherical cap suggests your perception is largely an illusion.
A very convincing illusion.
You're constantly playing the role of Observer 2, receiving a chaotic barrage of delayed postal rays, mathematically neutralizing the lag and retroactively flattening the universe, just to make it through the afternoon.
If we connect this to the bigger picture, the author provides a highly suggestive trail of breadcrumbs at the very end of the text.
The AI links.
Yes. They link to a series of dialogues they conducted with various artificial intelligence systems. And the titles of these dialogues are striking, specifically focusing on concepts like time thickness and memory integration.
Time thickness. That phrase really stuck with me.
It's evocative.
It implies that the present moment is not just a razor-thin point on a mathematical line. It suggests the present has literal depth, built from the overlapping arrival of delayed light.
And this raises an important question about consciousness itself. If the physical present is just an amalgamation of arriving historical data, then our cognitive experience of now relies entirely on memory integration.
The brain is doing the math.
The brain is not experiencing the universe in real time. It is acting as the ultimate Cartesian reconstructor, constantly stitching together staggered light signals to present a cohesive, flat illusion of reality.
It really forces you to question the very fabric of your daily experience. If the logical flat present you operate within is merely a reconstructed memory of delayed postal rays, how much of your reality is actually happening right now?
And how much of it is just your consciousness frantically flattening the complex, multidimensional geometry of the universe, bowing into imaginary dimensions, all so you can simply make sense of your day?
It is a staggering concept to mull over the next time you look at a clock. We'll leave you with that thought. Thanks for joining us for this deep dive, and we'll see you next time.